Stephen is an assistant professor at the University of Chicago in the CS department, and he is going to be talking about the Juniper Dual EC incident. Thank you. Sorry.
Hello. So I am Steve Checkoway, and today, or this evening really, I'm going to talk to you about the Juniper Dual EC incident. And if you don't know what that is, well, I'll jump right in and we can talk about it. So in late 2015, in December 2015, Juniper made a surprising announcement. They put out an out-of-cycle security bulletin saying that during an internal code review, they had discovered that some unknown third party had inserted some software into some of their routers. And that this led to two different security vulnerabilities. So the first was an unauthorized remote access, and the second is this somewhat vague statement that a knowledgeable attacker who can monitor VPN traffic is able to actually decrypt that traffic. So these are the devices. It's the Juniper Secure Services Gateway Firewall / VPN appliances. And the advisory was about a couple of versions of ScreenOS, which is their operating system that runs on these appliances. The first of these issues was the administrative access backdoor. And what's going on here is the attackers have inserted a hard-coded password highlighted in yellow here, where if you use that password to log in, then you are given administrator access. And this works both for SSH and for Telnet. And so HD Moore found this real fast. Like, the advisory came out, and it seemed like minutes later, he was like, here it is, we've got this. So this is pretty impactful, I think, since anybody can just use this password to log into any of these devices. There's some log entry that's made, but if you know enough to know that this is there, you can probably figure out how to get around that. You can probably erase that log entry. So this isn't what I'm going to talk about at all. Instead, I want to talk about the second vulnerability, which was this VPN decryption for some knowledgeable attacker. Now, what knowledgeable attacker means was not spelled out in the advisory. It's not clear from what Juniper has said what exactly it meant. And so the first hint of what this issue was came from running the strings program over one of the affected versions of their firmware and running strings over the fixed version and just doing a simple diff of these two. And you can see that we have some hex numbers here. These are just stored in strings. And really the only difference is in this bottom line here. And in fact, this was more or less the entire difference. So when Juniper put out their patch, all they did was they deleted this line and inserted that line. And that was it. So this is somewhat surprising. How is this going to be sufficient to allow passive VPN decryption? Well, maybe some of you recognize these numbers, but if not, you can do what I did and just Google them. And it turns out that the top 5 of them are some constants that are related to the elliptic curve P256. So from top to bottom, we have the prime P, and then we have the parameters A and B, and the x-coordinate of the generator and the group order. The last 2 lines, though, are somewhat of a mystery. Googling those didn't reveal any information other than the diffs that HD had posted. So I actually had to go and do a little bit of digging, and I was not the only one. So basically, once this announcement was made, a whole bunch of people around the world all started reverse engineering this firmware, trying to figure out what this is. And what it quickly became apparent it was a x-coordinate of a non-standard elliptic curve point. And the code that was using this turned out to be implementing the dual elliptic curve random number generator. So if you're not familiar with Dual EC DRBG, here's a bit of a timeline. This pseudo-random number generator was developed, or it was conceived of by the NSA in the early 2000s. And there was a real push to standardize it. It appears in, I think, at least 3 different standards, but ultimately NIST standardized it in 2006 in the special publication 800-90. The following year, some Microsoft researchers, Dan Shumow and Shumow-Ferguson, demonstrated that there was a theoretical backdoor in this random number generator. But nobody really paid all that much attention to it, since it turns out that this random number generator is really slow, and SP 800-90 has 3 other pseudorandom number generators that are orders of magnitude faster. So why would anybody ever use this? Well, fast forward a little bit, and Snowden documents revealed that, hey, maybe the NSA had something to do with backdooring this standard. And what came out a little bit later was that the NSA paid RSA $10 million to make Dual EC their default pseudorandom number generator in their BSafe library. I have a whole other talk about that. It turns out that that was a bad idea at the time. Eventually, we demonstrated that we could use this backdoor to compromise TLS in a bunch of different libraries that were using it, including BSafe. And eventually NIST decided, you know what, this was a big mistake. We should not have ever published this, and they withdrew it. And then last year, we showed that we can use Dual EC to passively decrypt VPN connections. Or rather, when I say that we showed that we can do it, we showed that other people had already done this in the past. And so this is what I'm going to talk about. So how does a backdoored random number generator work? I think we can all figure out how a hard-coded password works. You just enter the password and log in. But a random number generator seems like it's maybe too low level to figure out what's going on. So let's step through this here. So a pseudo-random number generator consists of a couple of parts. So we have some states. So S0 here is our initial state. And to these states, we apply a pair of functions. So f of S0 gets us a new state, S1. And g of S0 gives us our output, R1. Then, when we want to generate some more values, we just apply these functions again and again. And we keep going, and we can get as many pseudo-random values as we want, up to some limits. So how does a backdoor work? Well, if you have a pseudo-random number generator such that you can see some of the output from it, and from that you can apply some function and recover an internal state, then an attacker who is able to do this can predict all future outputs from the pseudo-random number generator. And this turns out to be a real big problem because a whole bunch of crypto protocols depend on having either values that the attacker can't guess or values that really need to be pseudo-random. Now, the EC in Dual EC stands for elliptic curve, so I have to do a one-page primer or one-slide primer here on elliptic curve math. So I apologize for this. It won't be too painful. Essentially, a point on an elliptic curve is a pair of numbers, x and y. And for the curve that we care about, x and y are 256-bit values. They're 32-byte integers. And points on elliptic curves have this rather curious property that you can add them together in a geometric fashion such that you end up with another point on the elliptic curve. How this actually happens doesn't matter. It's easy to do. You just perform a couple of simple arithmetic operations, modulo a prime. Very easy. And in particular, given an integer n and an elliptic curve point p, it is really easy to compute the product n times p, which is nothing more than p added to itself n times. And there are some fast ways to do it, but this is good enough. And the key to this whole work is that given points p and np, it is computationally difficult to recover n. So this is the elliptic curve discrete logarithm problem. And so this is believed to be intractable. In fact, we don't have any, for many specific curves, we don't have any idea how to do this. And in general, we don't have a great idea of how to do this, at least not in sub-exponential time. So let me walk through how dual EC works so that we can get an idea of how we can use this to break network protocols. So first, the internal states of dual EC are 32-byte numbers. And dual EC has a couple of fixed points. These don't change at any point. They are called P and Q in the standard. They are both generators of the elliptic curve group, if that means anything to you. But they're just some fixed points. So the way this works is first, starting from S0, we generate a new state S1 by multiplying S0 by P and taking the x coordinate. Since the coordinates are 32-byte integers, this works out perfectly. Then, to generate some output, we're going to take S1, multiply it by Q, and take the x coordinate. And then finally, for some statistical reasons, we don't use all of R1 here as our output. Instead, we take the least significant 30 bytes of R1, and that forms the most significant part of our output. And then this process continues. So we take S1, we multiply it by P, take the x coordinate, that gives us S2. Take S2, multiply it by Q, take the x coordinate, that gives us R2. Take the least significant 30 bytes of R2, and that forms the next 30 bytes of our output, and so on. So what Shumow and Ferguson discovered and revealed to everybody during the Crypto 2007 rump session was that if the attacker knows the relationship between P and Q, and by that I mean if the attacker knows an integer d such that P is equal to d times Q, then there is this pretty simple attack that can be performed to recover the internal state of the generator. So the way this works, you start with your output. The first 30 bytes of it form the 30 least significant bytes of R1. Then we have to guess the two most significant bytes, which really just means we try all 65,000 possibilities. And then we let R be an elliptic curve point whose x-coordinate is R1. Now, one of two things will happen. Either there will be no R, or there'll be two of them, and it doesn't matter which one you use. And if there's no R, then you just go and you try the next, you just try your next guess. So assuming you have an R, then what you can do is you can multiply that by D and take the x-coordinate. And if you have guessed R correctly, then that will, there we go. If you have chosen R correctly, then multiplying by D will give you the internal state S2. So you can either take my word for it, or you can read this chain of equalities down here that shows that this all works out. Now the attacker's job is pretty straightforward. The attacker doesn't know that they have picked the correct R, but we can use the remaining output as a way of checking. So the attacker just runs the generator forward, computes R2, takes the least significant 30 bytes, and compares it to the output. And if they match, then the correct guess has been made. And more importantly, the internal state S2 has been recovered. So what this means is that the attacker now knows all of the rest of the outputs from dual EC. So to do this, you might have noticed that the attacker needed to see some output. And more precisely, the attacker needs to see most of some output block, say 26 bytes of output, and some public function of enough of the following or of a following output in order to figure this out. So for example, if you have a network protocol that has a nonce that is, say, at least 26 bytes long, that gets sent over the wire, and it has a Diffie-Hellman public key that also gets sent over the wire, and the nonce was generated before the private key was generated, then this protocol is vulnerable to the Shumow-Ferguson attack. So how might someone go about learning the value d? So remember, fundamentally need to know this value d, which is the discrete logarithm of p. And I could think of 4 ways that an attacker could do this. One, the attacker could solve the discrete logarithm problem. Two, the attacker could be the person who actually picks the official elliptic curve point q. And one way that you can do this is you just pick a large integer e, multiply it times p, and then you set d to be the modular inverse of that. Three, you could use a non-standard point generated in exactly the same way. Or four, you can compromise somebody's source code and insert your own value of q generated in this same way. So I will just point out that one is probably too hard. We don't know how to do that. We do know that the NSA picked q, and we don't know how they picked it, and they're certainly not telling us. At least they're not telling me. Three, the non-standard point. It turns out that ScreenOS actually uses a non-standard point. I don't know why, and we'll come back to this point later on. And four, this is exactly what happened in this particular incident. So that one line of, or that one string that was changed, that was picking a different point q. And so based on this, we can make a pretty good guess. What was it that Juniper's knowledgeable attacker knew? Well, they knew the discrete logarithm d. That was fundamentally the thing that they knew. Now, this is actually really surprising because Juniper has said that they don't use dual EC in a way that could be vulnerable to attack. So they say they use dual EC, but it's not the primary random number generator. Instead, what they do is they use that to seed another random number generator, the ANSI X9.31 PRNG. So given this, it seems like there's a bit of a disconnect here. And so this raises a number of questions for us. So first, why doesn't the use of X9.31 preclude an attack based on knowing this value d for dual EC? Two, why does a change in Q actually result in a passive VPN decryption? And just because you have a backdoored random number generator doesn't mean that it necessarily follows that you have a broken network protocol. Third, what is the history of the dual EC? What is the history of the ScreenOS PRNG? So when did dual EC enter into this? Like, why would they do this? Four, are there any versions of ScreenOS with Juniper's Q that are vulnerable to attack? And finally, how was Juniper's Q actually generated? Well, it turns out that we are able to answer the first three of these questions. And the way that we can do that is by performing some forensic reverse engineering. So I reverse engineered, to a greater or lesser extent, 50 versions of ScreenOS over 5 major versions, and so 50 point releases over 5 major versions, mostly on ARM, but one x86. And so based on this, we can answer these first 3 questions. So let's take a look at the ScreenOS pseudorandom number generator and see if we can figure out what's going on here. So this is it. I have decompiled it using IDA Pro. I've removed a couple of things just to make it more clear, but let's focus over here on the right on PRNG generate. So if we read through this, some of the things that you might notice are that we have this conditional reseed. So as the generator is running, every now and then it will reseed. And we see that it's going to generate 32 bytes of output every time it is called. And it's going to do so 8 bytes at a time using the X9.31 pseudorandom number generator. So far, this seems to match exactly what Juniper has said. So let's look over at their reseed procedure. And sure enough, here is the 32 bytes of seed value that is being generated by dual EC. And the first 8 bytes of this become the X9.31 seed, and the remaining 24 become the key. It doesn't matter what's going on here, but it's using triple des, which is why we have 24 bytes. So this seems like this is exactly what Juniper described, and this shouldn't be vulnerable. But in fact, that's not the case. So let's take a closer look at it here. The first thing that happens is this global variable that I've called index. And keep in mind that none of these names are present in the binary. These are just ones that I've assigned to it. So first it sets index equal to 0. Then this function here, one stage RNG, it turns out it always returns false, which means that a reseed happens on every call. It's not really conditional. There is some way that it can be disabled, and this leads to an additional vulnerability, but you can check out the paper for the brief details about that. So since reseed happens every time, let's look over in the reseed function, and we can see dual EC generates 32 bytes of output, stores it in the global variable output. Then at the end of the function, it sets index equal to 32, and what that means is that this for loop never executes. So at the end of the generate function, output contains the value that was generated by dual EC and not any values generated by x9.31. So what's going on here? Well, for some reason, Juniper has reused two variables, two global variables. They have made their output variable be used both for dual EC, for reseeding x9.31, and also as the output of x9.31. And they have also made this index variable global for some reason. I don't know why. So it turns out a bunch of us were staring at this code and we were trying to figure out what was going on. And I was not at all the one who figured this out. So Willem there was the one who actually noticed that because of this reuse of the index variable, x9.31 was never running. OK, so now we're in a position to answer our first research question. Why doesn't the use of x9.31 defend against a compromised queue? Well, it never gets used. That's the basic reason. So we have these global variables. And so the supposedly main pseudorandom number generator is just never used. So what about our second research question? How is it that a compromised queue leads to VPN decryption? And for that, we have to talk about the Internet Key Exchange, or IKE. So IKE is used for securing, or for agreeing on traffic keys for IPsec, which can be used for securing VPN connections. There are two major versions of IKE, IKE v1 and IKE v2. They're more or less similar. There's some annoying differences, but basically they each have two phases. And in the first phase, they establish keys between both peers called the initiator and the responder. And the point of these traffic keys are simply to protect phase 2, where phase 2, they actually generate the traffic keys that they're going to use for IPsec or any other sort of encapsulated protocol that they're using. And in both cases, there is a really standard Diffie-Hellman key exchange that happens, although it's optional in phase 2. So here is a stylized version of an IKE Phase 1 packet. So it consists of a header followed by a sequence of payloads. So we have a security association payload, which contains details about what cipher suites are going to be in use. It contains a key exchange payload, which contains the Diffie-Hellman public key, and a nonce payload, which has a variable length integer between 8 and 256 bytes, which is just a random value. And then there are a handful of other payloads that are not so important for us. So I just want to point out that in ScreenOS, the private key X is generated via dual EC, and it is a 20-byte value. And the nonce is a 32-byte value that is also generated by dual EC. So this is pretty much exactly the situation that we need to be in order to do the Shumow-Ferguson attack. So in an ideal world, this is how the attack would proceed. So the nonce would be generated first, and we could just use the Shumow-Ferguson attack in order to recover the internal state S2. Recover the internal state S2, and then we just run the algorithm forward, and we can figure out our x value, and then we just exponentiate, compute g to the x, and we check, does that match the public key that got sent across the wire? If it does, then we're good. And if it doesn't, well, then we just try another value over here for our R1. Fortunately, this is the ideal case. And if we look at both the standard and the firmware, if you look at the code, it looks like what's going on is that the nonce is being generated after the Diffie-Hellman private key. And so in this case, there's no way to actually perform the attack and recover X, because we can perform the attack here with the nonce, and then that gets us S3, but we're too late. X has already been generated. And of course, we can't use X to run the attack because, well, if we had X, we wouldn't need to do this in the first place. We'd be all done. Now, it turns out that the reality is actually somewhere between the ideal case and the apparent case. So ScreenOS version 6.2 has a queue of pre-generated nonce and Diffie-Hellman key pairs. And there is a timer that fires once a second. And when the timer handler runs, it checks, are any of these queues not full? And if one of the queues is not full, then it will generate exactly one element and then stop and wait for the next timer to fire. And it turns out that the nonces are always filled first. So what this means is that the ideal attack usually works. There are ways to exhaust the queues or make it such that the nonces are generated after the private key. And in that case, you actually need to perform a multi-connection attack. And you can see the paper for some details on that. Now, unfortunately, this is not the end of the story. IKE has a number of authentication modes. So IKE v1 has 4 different authentication modes. It has authentication using public keys, using digital signatures. It has authentication using pre-shared keys. And it has 2 versions of authentication using public key encryption. And the case for digital signatures, the attack just works as described. For pre-shared keys, the attack works, but the attacker needs to know the pre-shared key. So if you have a weak key, then this isn't a problem. And if you have a strong key, then the attack doesn't work. And for the public key encryption, the attack simply fails because the nonces are encrypted, and we need to see the nonces in clear text in order to perform the attack. In IKE v2, the situation is actually more favorable for the attacker. The authentication modes play no role in deriving the traffic keys. And so that means the attack just works regardless of the authentication mode. So that's phase 1. So we have to, unfortunately, attack phase 1 and then attack phase 2. But once we've got phase 1, this is actually pretty easy. Some new nonces are going to be exchanged, and there'll be an optional Diffie-Hellman exchange. And your options here are either rerun the attack or just run the dual EC generator forward until you see the new value that matches the public key. In fact, we didn't even bother implementing the second one because the attack was so fast, it was fewer lines of code for us to write to just reuse the attack and just run it again. And so we did this. We purchased a NetScreen SSG 550M, and we created a modified version of the firmware exactly as the attackers would have done, although it sounds like they had access to source code and we were just patching binaries, but roughly the same. So I generated a Q value, and I told a graduate student, install this on the machine. And then, I mean, this is what graduate students are for. So then I had the student configure the several VPNs using a bunch of different modes. So we had it with IKE v1 using pre-shared keys, IKE v1 with RSA certs, and one version with IKE v2 with pre-shared keys. And it turns out the attack just worked exactly as described. So I had one student put the modified firmware on, and we had another student implement the attack, and the attack worked perfectly. OK, so now we can answer the second research question, which is why does a change in Q result in passive VPN decryption? Well, we know dual EC is used directly for the outputs, so we can just run the Shumow-Ferguson attack, and it works, at least for some VPN configurations. So what about the third question? What is the history of the ScreenOS PRNG? And on the left, we have the some key points about ScreenOS version 6.1, the last revision of 6.1. And it has the ANSI X9.31 pseudorandom number generator, which is reseeded every 10,000 calls. And the seeds appear to come from some entropy that is gathered during interrupts. It has a 20-byte IKE nonce, and it has queues of Diffie-Hellman key pairs. So there's some of these pre-generation queues for the key pairs, but not for the nonces. By contrast, the first revision of ScreenOS 6.2 introduced Dual EC as part of this somewhat broken cascade between Dual EC and then X9.31. It reseeded on every call. And this reseed bug, this reuse of the global variables, causes Dual EC output to be exposed. And for some reason, the IKE nonces were changed from 20 bytes to 32 bytes. And lastly, the nonce pre-generation queues were added to this. And so in my mind, these differences raise a number of why questions. So why was Dual EC added? Well, I can't think of any good engineering reason for this to happen. In fact, doing this, adding Dual EC, meant that they had to add a whole pile of elliptic curve crypto code that wasn't used for anything else, just for their pseudo-random number generator. This actually changes in version 6.3, where they use it for some other stuff. But in this version, this is the only use. And I can't think of a standardization reason for using Dual EC. Sure, X9.31 was an older standard, but they were FIPS certified for X9.31, and they never got FIPS certified for Dual EC. So I don't know why they did this. Next was the reseed. So they've changed from having this reseed counter, which gets incremented until it hits 10,000, and then they do the reseed, to, in 6.2, they have the reseed counter, which is only ever incremented and then set to 0. It's never checked or in any other way used, and it reseeds every time. So why does this happen? Well, I can't think of a good engineering reason, and I can kind of think of a cryptographic reason. Maybe they're trying to do this for backtracking resistance, or it could just be a bug. I don't know. Speaking of bugs, there is the fact that the output and the index variables are global in 6.2. And if you look over in 6.1, you can see that the index variable was a local variable. So when they moved from 6.1 to 6.2, they changed this variable from local to global. And it's baffling. Similarly, the output goes from being an input to PRNG generate to being this global this global value. So why would they do this? Well, again, I can't really think of any good engineering reason. It could just be a bug, but if so, it's a really strange one. I've never seen someone just make a local variable global and then reuse it in functions that were essentially unrelated. I'm not sure. So what about the IKE nonce size increase? Well, I can't think of a good engineering reason for increasing the size from 20 bytes to 32 bytes. And I can't really think of a good cryptographic reason for doing it. A 20-byte nonce is more than sufficient. The DoD apparently claimed that public randomness for each side, they were talking about TLS here, should be at least twice as long as the security level for cryptographic parity. But they don't explain what that means, and although I'm not a cryptographer, I like to talk to cryptographers, and none of them have any clue what this means either, and they don't have any idea why this is. So I can't think of a good cryptographic reason for doing this. But I will note that at 20 bytes, the Shumow-Ferguson attack takes 2 to the 96 scalar multiplications, whereas at 32 bytes, it takes 2 to the 16. So by going from 20 to 32 bytes, they have made the attack easier by a factor of 2 to the 80, which is amazing. And then finally, we have these pre-generation queues. So 6.1 has Diffie-Hellman key pair queues. And this is actually pretty reasonable, I think. So it's moderately computationally expensive to perform a modular exponentiation. It's not that expensive, but there's some cost to doing so. And in 6.2, they added the pre-generated nonces. And I can actually think of a pretty good engineering reason for this. So Dual EC is about 125 times slower than X9.31. At least that was true on my laptop. And I had, I tried to write an implementation of Dual EC that was pretty good. I did the best I could. I wasn't using OpenSSL, which is what they were doing. So, it's probably even slower on these appliances. So it's probably the case that they implemented Dual EC and they were just testing it and they realized that VPN connections were established noticeably slower than before. And they probably figured out, well, this random number generator is slow, so they thought, well, we'll just generate these in advance, exactly as we do with our Diffie-Hellman keys. So that kind of makes sense to me, although I think I might not have gone with this random number generator if it was so much slower than what I had before. So if we look at these in aggregate, what we see is that these first 4 changes were actually required for VPN decryption. Had any of them not happened, the attack would be either impossible or, in the case of the nonces, just infeasible. And the final change, the nonce pregeneration queue, enables single connection decryptions. Without that, you have to use multiple connections. OK, so what's the history? Well, in one point release, they made a whole bunch of changes that enabled passive VPN decryption. So what about our other questions? So are there any versions of ScreenOS using Juniper's Q value that are vulnerable? Well, that depends. So it depends on how Q was generated, how their Q was generated, and who knows the value D. And so how was their Q generated? They're not saying. And they could, at least in theory, they could do something like, say they took their CEO's birthday and they ran it through SHA-256, and they said this is going to be the X coordinate of Q, and we'll just figure out what the corresponding Y coordinate will be. That would be totally fine, and there would be no problems. But they haven't said anything about this, so there's nothing that I can say about it. All right, so what lessons can we draw from this? And I think that there are several, so I wanted to highlight 4 of them. One, pseudorandom number generators are really critical to network protocols. So you should maybe consider doing something like hashing your random number, your pseudo-random numbers, before you're putting them on the wire. And if you're writing some code or you see some code that is changing your pseudo-random number generation implementation, you should scrutinize that closely. You should try to figure out, why is this changing and what are the implications of that? And you might consider using different PRNGs for your public random values and your private random values. At least in theory, that's a great idea. In practice, maybe you don't want to do that for some engineering reasons, and you should, just call into your operating system and say, please give me some pseudorandom values. Second, you should not allow your nonces to vary in length or be longer than necessary. So IKE's 256-byte nonces, or at least that's the maximum size, are just unnecessarily long. And having a long or a variable length nonce is just asking for someone to either intentionally or accidentally reveal some information by way of that nonce. And it's worth pointing out that variable length nonces actually allow fingerprinting of devices, so you can figure out if one particular implementation always uses 20 bytes and another always uses 32, then you can make some guesses as to what's going on. Third, you should include even low entropy secrets into your key derivation process. So IKE v1's pre-shared key was actually more secure than IKE v2. And this is a terrible situation to be in. We should be moving from less secure to more secure. But here, that was unfortunately not the case. And finally, the NSA has this notion of NOBUS, which stands for nobody but us. And this is something that they use, according to them, to describe flaws that they think can't be exploited by anybody but them. And Dual EC is indistinguishable from a building block of a no-bus exceptional access mechanism. So law enforcement wants ways to get into your phone or see your communications, and so they want exceptional access. And Dual EC is one way that you could consider building such an exceptional access, but I think that this incident is a clear warning of why that's a bad idea. Whether or not Juniper did this intentionally, I can't say, but what I can say is that an attacker was able to come in and change one string, in essence, and turn that exceptional access into attacker access. So you definitely don't want that. And so I think the main lesson that we should learn is that you really should not be building exceptional access into your network protocols. Right. So with that, I'm all finished, and I'd be happy to take any questions. Yes?
Have they since changed the global variables?
So the first thing that Juniper did was they patched the systems back to their original version, and then they removed Dual EC altogether, according to them. I don't have a copy of any of the most recent firmware, so I haven't verified that myself. Yeah.
How are the attackers able to insert their queue in source?
So how are the attackers able to insert the queue into the source code? That's a great question. I don't know the answer to that, and I do know that some reporters are very interested in finding out the answer to that question, but Juniper has been quiet on this front. Yeah.
Kind of along the same lines, why Juniper and not Cisco or not like anyone else? Or I mean, have we even been able to rule out that other popular, more popular? I mean, because Juniper is not like the most widely used vendor out there.
So the question was, why Juniper and not another vendor like Cisco? And the answer is, I don't know. It's possible that other vendors have similar issues, but I'm not really in a position to say. There was some great work that was done recently by a number of my co-authors here on the duck attack, if you have heard of this. This is the don't use hard-coded keys. And it turns out that a number of people were using, including other VPN vendors, were using the ANSI X9.31 generator with hard-coded keys, and that this leads to basically trivial decryption. So it's possible that some of these other vendors just already had problems, or maybe attackers have gone after the others and we just don't know yet. Is the 931 based on triple DES? So the original version was X9.17, and I believe that was based on triple DES. I don't remember if 31 specifies triple DES or not, but I think people are mostly using AES for that.
Fourth question. Did Juniper ever say that they actually implemented Dual EC?
Did Juniper say if they implemented Dual EC?
Is that code that they added? I know they released. We looked after the Snowden documents. They looked into their implementation. They said we use X, but did they actually verify that they actually implemented Dual EC originally? Like, is that their code? Do we know?
Oh.
They made so many that all has to happen for this to be vulnerable. It seems.
Right. So did Juniper implement Dual EC in the first place? I hadn't considered that. They haven't said, to the best of my knowledge, the elliptic curve code that was in there didn't come from OpenSSL, although it does print out some string that makes it look like it comes from some version of OpenSSL. I don't know. That's a great question.
Someone should ask that.
I agree. Someone should ask that.
To the same point, like, all the changes that were made were so weird, and apparently somebody was able to insert their own queue. They could be the same person or the same party.
So all of the changes were so weird, and someone was able to insert the same queue, so they could be the same party. Maybe, but I actually kind of doubt that, because if you as the attacker had the ability to put this code in the first place, it seems like you would use your own, you would use a queue that you knew the corresponding D value for. Now it's possible that one party did this and then another party took advantage of it, neither of which were Juniper. But again, I don't know.